So, are we all in place? Okay, let's get started. So this is the session for connecting the IoT to FIWARE. And first of all, I would like to invite the speakers here. So Daniel, can you come? Gilles and Enroe. Okay, so I think now we can get started. I will be giving the presentation on the introduction, right? So how we connect the IoT to FIWARE, very brief and high-level overview. Then my colleague Daniel will introduce the IoT agents, which is the main piece that together with the NGSI brokers is able to push the information to the FIWARE. And then my colleague Enroe from NEC will introduce the IoT Broker, right, which is a IoT-specific NGSI broker, right, and it extends the capabilities for the IoT context. And then at the end, so last but not least, Gilles Privat from Orange will introduce a solution of a NGSI broker for the IoT Gateways, right? So his presentation will be focused more on the IoT edge. That is one of the points where we are evolving. So this is all. I would like the session to be quite interactive. So when you have questions, feel free to interrupt us and make questions, or you can wait till the end or grab us in the corridor if you feel shy. And let me go first with the introduction. So lately we hear a lot about the smart application areas, right? We hear about smart cities, which is municipalities trying to get IT technologies to deliver new services to the citizens and even to create new businesses. We hear the same now, or we start to hear the same for the smart agri-food sector with the smart agri-food concept, where the IT technologies want to develop services that help the producers in the agri-food environment to be more efficient or even to be able to deliver products in a different way. Then we have smart regions, which is a number of municipalities get together and then they try to deliver services similar to the smart cities but to a wider region, right? Some number of municipalities together in the end. And then we have the very key topic of a smart industry, which is applying similar technologies, but in a different way to the Industry 4.0. All these technologies, all these areas of application are possible because we have some emerging technologies that are bringing a lot of changes. The first one is the Internet of Things, right, which is the subject for this session. And the Internet of Things allows us to put a lot of sensors and actuators on the field and then retrieve a lot of information, so perform monitoring activities in a different way and also to be able to control the processes in a much more efficient way. It brings also a lot of data to the ecosystem so that new businesses, new ideas and new solutions may arise. Then we have the cloud infrastructure, which allows any provider to deliver in a very fast and efficient way new services from the cloud. You know this very well. We have the big data and analytics in general, that this is one area of application that is, or one technology that is growing quite fast. And finally, we have the mobile application ecosystem, because we shouldn't forget that in the end, we have in our pockets a computer, a very powerful computer, that is able to access these cloud services, etc. But with all these things, we are still missing some pieces. And one of the pieces that we are missing is brought by FIWARE, and it's the interoperability. So the $1 million question is when IoT interoperability or smart application areas interoperability will happen. And the answer to this It's not very easy because you can't see in the image, but that was the purpose. You can see how many alliances and standardization bodies are working on this, right? And it's quite hard that interoperability will come out from all this mess. So our vision that started a couple of years ago is, our vision is to provide this interoperability at the context data level, right? In the end, IoT resources are data resources, right? So we can model the reality of IoT with entities. This has been quite well explained by my colleague Fermin before, so I will not extend on this. But from the IoT perspective, the main point is that we are providing exactly what developers and data scientists, for instance, would like to see from the IoT, because they are interested on the data, right? And maybe they are interested to push information, so they trigger actions and commands. But at that level, they are not that much interested in the device management, in the IoT-specific networks management, etc. There is a place for that for integrators, of course. But in the end, at the data level, which is the level that we believe the interoperability can be provided today, this is not the need. The need of the developers that we tried to satisfy from the very beginning was first to have a common language for all the data sources, being IoT or not, because when you are developing a new application or you are developing a solution for a vertical in a smart city, you are interested on the data source and the data that is providing in real time with access to the historics, etc. The developers are also interested on having a single REST API, single API in general, but it fits REST better because it's more simple and it's what they are used to nowadays. So they just want to query the data, subscribe to changes in the data, and trigger actions, right? And as you saw in the presentation of Fermin, this is very easily done from the API of the context broker. And you know that we are delivering open source solutions, and what the developers want in that area is that we use the same tools they are used to, the GitHub, read the docs for the documentation, etc. So this slide will appear many times in the event, I believe, because the core of FIWARE, and it's also the same way in the FIWARE IoT, is to gather all the data in a context data ecosystem, right? So in this case, you can model the users that live in a city, you can model street devices, you can model also the public transportation system, etc. And with this, you can infer the KPIs that the municipality is interested in, etc. And what is the difference in our approach and what was happening time ago? Previously, the smart asterisk or any smart application area was made of different silos, right? Or we call them verticals in the smart city arena. You had, for instance, a service for the garbage collection, monitoring, you have the water monitoring from the municipality, you have the energy saving and monitoring as well, and in each of them, you had several devices, if there were devices, right? Because sometimes it's not related to IoT, but we are considering IoT now. Then these devices are connected to the cloud normally or to some data service using some specific communication technology. And then you have some kind of intelligence to deliver a dashboard with the KPIs that are needed, or you have some data analytic techniques so you can infer conclusions and maybe send notifications to someone to control something, etc. And then you had this standalone solution for each one of the verticals that you were delivering to a city in this case, right? But it's the same for smart agri-food or smart industry, etc. The point here is that we were getting higher efficiency because in the end you are bringing automatization, right? So normally the common suppliers that were dealing with municipalities on these services, they got more technology, right? They were using new technologies, and then the services were more efficient and you could control more things. But this is not the main purpose that we are looking for, because that brings efficiency, but normally it's just that, efficiency. Maybe it's even for cutting jobs in the end, because you have to send the person less times to monitor the city systems or to monitor the garbage containers, etc. our vision tries to deliver a growth engine in a local way for all these scenarios, right? For smart cities, for smart agri-food, etc. The point is that you can only do this if you lower the barriers to enter for new suppliers, right? I'm not talking only about the startups, but they are in, of course. I'm not talking only about entrepreneurship, but we are talking also about new suppliers because new ideas will come. Why? Because in the end, you bring more efficiency because you can share the same communication technology, the same connectivity for several devices from different verticals. But the most important, with an IoT agent, you will adapt the specific IoT technology they are using or the specific IoT protocol they are using, and you will bring all this information into the common and standardized NGSI data ecosystem, right? So then, for developers, for third parties willing to deliver a service, or for data scientists, there is a common place to get all the data or to retrieve all the data in a standard way, right? Sometimes this data will be open data, right? We have many cities that day by day, they are willing to deliver more open data to the citizens. We have experiences with the smart cities where the mayor of the city sometimes tell us, all right, so I was able to put all the data, all the open data that I have in the city, for instance, in a website. And yes, the citizens were interested in the beginning, they were accessing this, but in the end, when the hype is over, nobody else is accessing there, right? Because you have to provide the data, not raw data or processed data to the citizens, you have to provide this to developers of applications, you have to provide this to data scientists, etc. And the only way to do this in an efficient manner is to have a common standard for that. And this is the main idea. In the next presentation, my colleague will explain how you can connect, for instance, devices with a specific IoT agent. He will go into the details of the API. But we have different flavors of IoT agents. We don't believe that, at least at this point, will appear an emerging technology for all, right? There will be very different solutions because in IoT, there are many different conditions. There are constrained devices, for instance. There are places where the mobile connectivity is not available, so you have to use other kind of networks. There are new IoT networks arising, like LoRa, like Sigfox, etc., and they are changing continuously as well. But we believe that in the end, you will be able to adapt all these specifics into the data ecosystem, and you will evolve with them. This is not fixed, right? This is a living creature, and we are creating new IoT agents, and moreover, we provide a library so that you can create your own IoT agent, and this can be done in few days for developers. So in this part, we have higher efficiency because you also share the cloud infrastructure for many verticals, but also, in the end, you have the possibility to have cross-vertical ideas. This is the main point. And this is how the most used IoT stack looks like, because you know that in FIWARE you have different generic enablers, and you can use them optionally, so you don't need to get all them to build up your solution. But this is what we've seen that is more useful for the IoT integrators, developers, etc. You have the IoT agents that translate the specifics into NGSI. Then you have a broker. Normally, we've seen the context broker or ION context broker for these kind of use cases. Then for the historics, you use different databases connected with the Cygnus. For instance, CCAN for open data, Hadoop, or the short-term historics component that we deliver as well. And then you have the intermediation of a PEP proxy, right, for security reasons. So only the people or the developers that may access a specific subservice of a service may access these resources, or maybe they can perform certain operations, but not others, maybe read but not write, etc., or not create. I wrote a very easy decision tree on the IoT agents, right? Daniel is presenting later the ones that we have so far. The first question is, you can develop code for your devices or not. Maybe you can't because the devices are so constrained that you cannot do that, or maybe it's a closed solution, or maybe you're just lazy. If you can't code a specific protocol and it's not supported by us, then you have to get the Node.js library that we provide and develop your own IoT agent. But this is really a very easy task for experienced developers. If you can code for your devices, or you support some of the protocols that we are using, we try to support the standard protocols, then you need to ask yourself if you are using constrained networks, constrained devices, etc. If you are doing so, then you should be using very light protocols based on UDP, like OMA, lightweight M2M, etc. In lightweight M2M, there is also some device management, but we have implemented so far only the way to send data. And if your devices are not that much constrained, then you can use JSON to communicate with your devices, or a text-based protocol that we call Ultralight 2.0. And you have different alternatives for the transport. You have HTTP transport, or you have MQTT transport. And this is the ongoing work that we have in our plans. The first thing is the evolution of the IoT agents, so include new functionalities. So our team, for instance, is working in data transformations, so you can adapt the data model of the devices to the data model that you want to have at the top in the broker. We are developing, or we are considering new protocols, but we will do as they become de facto standards, right? Or maybe they are provided by the community. And we will have a look to the IoT management, but we didn't so far because the landscape is quite complex, right? So this is normally addressed by IoT integrators, but of course the first consideration we will make is to implement the management functionalities of lightweight M2M, and to maybe to be compatible with the management systems of some IoT networks, like the mobile M2M network. Then we will go from a cloud centralized model, like the one I presented, to a more distributed model, because for many scenarios, they are requesting that the decisions are taken first at the gateway levels, and then maybe the data is pushed upwards to the cloud. So we are starting to test how the IoT agents that we have today may run in the gateways. There is a version of the context broker, a lightweight version that runs even in a Raspberry Pi that has been developed by Orange, and Gilles will introduce that. And we have even a CEP that is working for that, a complex event processing. So you have all the intelligence in the gateway, although later you send the data up to the cloud. Then we are working in the data models. In the smart cities, the OASC Alliance that was mentioned this morning, and the smart agri-food, we have the Internet of Farm and Food project, that is the flagship project on smart agriculture, that is starting in January next year, right? Both DG Connect and DG Agri are funding this project, so we expect a lot of visibility on the results and the data models that we will create here. Then we are investigating the federation and more specific IoT NGSI brokers, like the one that NEC will describe later. And we are working also in the market dynamization, because you need devices to support the standards that we are considering in FIWARE. It's not very difficult because we are using common standards from the market. But we are involving the device makers to providing their websites, the instructions to configure their devices so that they can very easily be plugged into FIWARE. We call this the FIWARE IoT Ready program. If you look for this in Google, you will find the page. And we have up to 15 device vendors. And we expect to grow quite fast soon. This is all from my side, and now it's you may have the questions now, or you can wait for later on. Maybe it's better at the end. But if there is something, all right.
I will try to give you a very quick and brief introduction about what the IoT agents are and how they fit in the FIWARE architecture. First of all, the main purpose of the IoT agents is to serve as a kind of translation layer between the devices in the southbound that are typically constrained systems that use specific protocols like CoAP, MQTT, and so on. and the core of our platform, that is the NGSI context broker. First of all, when a project involves extracting information or acting with a device, it will interact in two ways with our IoT agents. First of all, before starting sending information or starting sending commands to the devices, all the projects that are using those devices must register them in the IoT agents. In order to do so, the IoT agents provide a Northbound API for the registration both of groups of devices and of singular devices. And in the process of that registration, we will see that the customers or the companies that are creating those projects can set the properties of those groups of devices, like security properties, the API key or trust tokens used for accessing the data, as well as mapping the information from the devices to the representation that information will have in the NGSI context broker. First of all, when we design the IoT agents, we have several principles in mind. We wanted them to have to be modular and stateless, so we can change the way we deploy the IoT agents. We wanted to be able to have different architectures, horizontal scalability, and so on, deployment flexibility. And also, we wanted to ease the creation of the custom custom IoT agents. If you have devices that don't use a particular protocol that is already implemented in our IoT agents, we offer a library in Node.js that will easily give you the ability to connect your protocol, protocol for your specific devices to the platform, while giving you all the abilities, the default abilities that all IoT agents have, like registration of devices, registration of groups of devices, model transformations, and so on. I will show you now some examples of how a group of devices is provisioned, of how a device is provisioned in the platform. The Northbound APIs of the IoT agents are mostly based on REST designed architecture, and you will have a different resource for the groups of devices and for the devices themselves. This payload you see on the right is the payload to create a very basic group of devices. You can see in the payload that the only two important things that are specified are an API key that all the groups of devices must define in order to assign each device to that group, and the type and the protocol that device will be using. Whenever the device is going to send information, it will indicate two pieces of information to the IoT agents in order for the IoT agent to know how to map the information it's coming. One of that pieces of information is the API key of the group of devices the devices belong to, and the other one is the device ID you will give in the registration of the device itself. As you can see, when you register a device ID, you can define some information about how the device ID data is going to be mapped to the entity data in the context broker. Here, we only see the entity type information, but you can also specify entity type, entity name, and a lot of different ways of specifying the attributes of the entity. In the attributes section, you will specify the mapping between the names of the attributes in the protocol, the southbound protocol data payload, and the name of the attribute that specific data will be mapped to in the NGSI entity. In this case, we have a southbound attribute called lum that will be mapped to an NGSI attribute called luminance. We can also define the type of the attribute in the NGSI entity. Along with the definition of this basic information, the IoT agents provide the capabilities of data model transformation in order to let you combine some of the information coming from the southbound protocols into different higher level entity attributes. And it will also let you map different the same data to different entities, not only the default device entity. One thing that I didn't mention before is that each device will be mapped. Typically, each device will be mapped to a single device entity in the NGSI context broker. But that default behavior can be overridden with the provisioning of the device. Here I will show you a small example of how information, once the device is provisioned in the platform, how the device can send information to the IoT agents. In this example, we will be using the Ultralight 2.0 HTTP IoT agent. The same, most of the IoT agents offer not only offer a single protocol, a single southbound protocol, but different transport for that protocol. In this case, we use HTTP, but the exact same payload could be used with MQTT or other protocols in order to get exactly the same output in the NGSI part. As you can see, with Ultralight 2.0, the only thing you have to do in order to report some information, in this case, is some information about parking spots, the occupancy of parking spots, and a luminance sensor. The only thing you have to do is to send a simple post to the southbound endpoint of the IoT agent, indicating two pieces of data, as I told you before. The API key you defined in the group of devices, and the device ID you defined in the provisioning of the device. That data will be mapped to the NGSI device, to NGSI entity representing the device in the context broker. The retrieving and sending of commands is quite similar. In the case of the IoT agents provide different ways of interactions, and in the case of the commands, when you want to send a command to the device, you can either define an endpoint for the device in order for the IoT agent to send the command directly to that endpoint. In that case, the IoT agent will post the payload you have below directly to the endpoint you have defined, or you can define the commands as pull commands. And in that case, the IoT agent will return the information of all the pending commands for each measure the device has reported to the IoT agents. So the device can retrieve the commands whenever it's available. For example, if a device is sleeping for a very long time, it will retrieve in the next time it will report a measure. It would retrieve the pending commands that have been generated all the time where it was asleep. In the case of the polling commands, that piece of code is a return for that specific case of a pull command. And well, all of this, all the information about the IoT agents, about the IoT agents in general, can be found in the FIWARE Catalog. and you will find links to all the IoT agents of the different protocols, as well as the IoT Agent Manager and so on. There is a special repository that is the one of the IoT Agent Library. In that repository, you will find not only information about how to develop an IoT agent, but also a lot of general information about how the IoT agents work, and the definition of the northbound APIs of the IoT agent, those that let you create groups and provision particular devices. And so with this I finish, and I give the turn to Gilles.
So we are waiting for the right presentation to come up. Here it is. And I'd like to present you the IoT Broker component within the FIWARE protocol stack. And the first question you're probably going to ask is, oh, there's a context broker, and now there's an IoT broker. What is this, and what is the difference between two things? And the good news is, first of all, on one hand, it's the same thing, because they're talking the same APIs, and you can use it more or less interchangeable at different things. On the other hand, it's completely different, because the IoT broker is targeting towards IoT scenarios where you are not looking like in a data-centric view where all the data is pushed into a cloud and the cloud is going to handle that, and you're not caring about how the data is gathered, whether the local networks are overloaded and the energy consumption of the devices. You just assume the data is there. And for this relatively simple data-centric, cloud-centric model, the Orion broker was developed. For the IoT broker, we are looking now at more complex scenarios where we are looking into IoT networks, we are looking into the requirements of what IoT is needing, and how in the future smart cities are using IoT networks for their purposes. And I'd like to introduce a few advanced systems once this is going to work, which is not. Was this going forward? Yeah? Okay. Maybe somebody at the back can press for me. Can you press for the next slide? Also of this thing here. Oh, just turning it around. Thank you. So easy. So you see, technology needs to be made for the people who are using it. We want to take a look at some of the advanced features of the IoT broker, especially how we are incorporating semantic knowledge into the brokering process. We are going to look into federation aspects here and into scalability. And at the end, I would like to look into some real-world scenarios which we're currently looking in, and into FogFlow, which is our edge processing extensions to FIWARE. So first of all, to give you a picture where we are, the IoT broker, as you see, is part of the IoT backend. It is reporting data to the Orion context broker. It's using the same API, and that's what I said. You can use it interchangeable, because wherever an IoT agent is reporting into the IoT broker, he can also report into the Orion broker, because the APIs are the same and can be interchangeable used. Now the IoT broker is adding additional command flows through the system and additional features which we are going to tell you in a minute about here. So that's where the IoT broker is allocated in the overall architecture of the FIWARE chapter. And later on, when Gilles is presenting, he's going to explain you how we are handling edge processing on the edge and complex event processing here. So very fast, the IoT broker is collecting from the devices, from the gateway, from other sources of the IoT system, data, is providing and mapping that into what we call the thing level. So instead of having a single sensor with its ID and its very technical information, we like to be able to talk about the things, the car, the houses, the computer. And the IoT broker is doing this mapping by moving into the NGSI API plus using the respective data model. And we are executing then the information queries on behalf of the application. And you've seen in the Orion broker, the information query was a simple query towards the locally stored last value of the information. In the same way, we can do an access to local stored information in the cache. We have, for example, a plug-and-play component which you can add to the broker for a big data store where you can keep the complete history of data, but you can also forward the request to the devices and the gateways. And that allows you to have what we call the silent Internet of Things, where not every sensor is all the time sending the data up to the cloud, but we can forward and query the sensor at the right time. And of course, we can mix and merge the different models, because in some times it makes sense to send all the data up to the cloud. Sometimes it's better to keep the data low because you only need it from time to time. IoT Broker is implementing this different semantics of the execution and allows you to do that. In addition to that, we have advanced discovery operation. Coming to that, what I mean with advanced in this later chapter. And we are collecting and aggregating in the broker already information. We are not leaving that to the apps. Or let's put it this way, some things we are doing in the broker, some things the applications are doing because it's domain-specific knowledge. Now, skipping that because of the timing, you see that we have the subscribe, notify, and the thing level information, which is representing by having different naming schemes, by having typing of the information objects and adding the context information, which we all think is very important, and then having discovery and resolution operation to find the devices here. And some advanced features which you can find up in our documentation on association and entity compositions. I like to talk about this protocol stack of the future, which we think is happening. We think that, you have seen that in Carlos' presentation, there are thousands and thousands of different IoT development systems. And all of them are trying to make an abstraction of the hardware and trying to have a protocol for delivering the data. And some of them make sense because they're directly integrated into Windows, or they are on some other areas and they cover an industrial automation system, but they're all very different. There's an emerging international standard called 1M2M, which is happening, which is on one hand standardizing a lot of the interfaces towards a low-level implementation. On the other one, give you a very precise service, and it's basically shipping a data container from A to B. But you don't know what's inside of the data container. And that's exactly where OMA NGSI, the IoT broker, the Orion context broker is coming in, where the information is getting out of pure data, which is shipped from one side to the other, to data, to information that is understood and can be used. And this is where the IoT broker and the Orion broker is coming in, where we can also handle the big data aspect of it. And we think that on top of that, domain-specific agents will pick up the information which they are needing and make that into semantic annotated information, into knowledge, and do processing on site. And we have, in the upcoming years, new projects which are looking into these architectures. On one hand, an EU-Korea call and an EU-Japan call, where we're looking into these kind of city platforms as a service. And we have the large-scale pilot on autonomous driving, which is using this architecture, 1M2M for the pure data transfer and NGSI for the understanding of the data in the large-scale pilot. Now looking at the advanced features of the IoT broker. First, knowledge processing, how we are factoring knowledge into the data model, the federation aspect, and the scalability aspect. Knowledge. Basically, in the IoT world, one of the key characters of the future is that we want to have an open system where thousands of sensors from very different vendors, from very different users should be integrated into the system. And it's very important to understand them, to understand the context. And that's where we need to have knowledge. And that knowledge needs to be represented and made operational, and we should be able to query it. That's why we introduced recently the IoT knowledge server into the picture. And that is then collaborating with the IoT broker in having advanced features for lookup and improving the way what users can do. In addition to that, we can store static and dynamic knowledge about sensors and their relationship to other objects inside of the triple store in the knowledge server. Let me go directly to what we are doing. We have predefined queries, which is helping the IoT broker to find objects. As an example, we have subtyping relationship introduced, which allows you to, for example, say you have a temperature sensor and a movement sensor and an air quality sensor, but they are all sensors. And you would like to model this kind of subtyping relationship, and then in your queries, you want to be able to use that subtyping relationship. Being it, I'm searching for all kinds of sensors, being it, I'm searching for all kinds of cars, or whether I'm searching for a Mercedes car or a BMW, I don't care. I want to have that modeled and executed as part of the queries. And that's what the knowledge server is adding. And we have some advanced functions, like we can add new queries into the knowledge server, we can have Sparkle queries and others. To give you a view on how that is looking like, I have an IoT broker. He is asked to execute a query like give me all sensors from Tokyo. He is making a query, what sensors could there be? So I'm trying to understand what are sensors. I'm looking into a cache, but the cache is telling me, no, I don't know which other sensors or which other sensor types might be there. Then I'm looking up in our internal architecture into a small database, which is basically storing what kind of query do you need to execute to find the subtypes of the type sensor. I will get that returned. That is then sent to an Apache Gina Fuseki triple store, where all the information is stored about the sensors and the typing information here. There it is executed. I get returned that my system knows about temperature sensors, about noise sensors, and about light sensors, which I can then return, and then my query execution will not only find the temperature sensors, but will find all these kind of sensors. And you can imagine that this simple example can be extended to much more complex things. So that's where additional function is added to the broker part here. And of course, we are storing that in the cache, and that's how the broker is using it. He is now, as you see here, checking for the different types, the generic sensor as well as specific sensors here in a single query, and you can easily extend the database and add your new knowledge to it. Yeah. So that was the knowledge server, and one example how the knowledge server is being used in the system to answer to some of the requests. The next thing is about brokering, meaning we are looking into federation of system. As an example, in our commercial systems, we are using FIWARE in some of our commercial installations. We are surprisingly having a lot of new services being developed in New Zealand. We have some smart waste and other commercial operating services in Europe, but we have a range of new services in New Zealand, and we are still operating our cloud from the Madrid data center. And we are more and more getting the information from down there. But we are understanding that, though the international lines are working quite well, we still need to deal with this federation aspect. So basically, we're looking into substructuring our IoT platform into a central data hub and then local data hubs, and using again NGSI for combining these systems together, like you're being shown here, so that you have applications which can access the information, which then can access the information in the local system. And of course, as shown here, we can not only have this hierarchical structure, as you have seen, but we can mesh up the different IoT brokers together and then have applications and each of the different brokers accessing the local view on the system, as well as doing international or worldwide queries here. So that at the end of the day, we are being able to provide a federated system which can provide you with information from all around the world with these federated structures here. And you see inside of the protocol implementation, we have some sub-features for efficiency improvement, broadcasting, selective communication, that we're not always asking the complete broker world, but only forward the request to a certain part, loop detection for efficiency in other areas here. Scalability, basically, we're expecting that the number of devices is going to increase, but as well the number of applications and the number of queries which we're doing toward this. So basically what we need to do is we need to scale the IoT broker. Very simplified speaking, we have created stateless brokers which are externalizing its state and which can be replicated, and where we can ask the queries to each of the broker is then executing the queries, including, for example, the federation. And whenever you need more horsepower, you can add more brokers to it, and then the queries will be executed here. That's what we're needing to deal with, the amount of devices increasing as well as the amount of clients increasing here. Now looking at some of the scenarios where all of these pieces are coming together. One is we're looking at a smart city magnifier, which is an application which should enable users to really look into a city and find out is there a critical situation, what are the current statuses there, and very fast integrate the situation together. We've showcased that at the ETSI M2M workshop 2 weeks ago, and basically you see it's collecting data from many different cities, from many different sensors, not all coming from the same vendors. In order to deal with the heterogeneity of this data, we are running the system through what we call the morphing mediation gateway, a gateway which we can dynamically extend with functionality. That's research in the device IoT project. We're getting data from Korea, from Paris in France, from Santander in Spain, from Guildford in the UK. Very soon we are going to get data from Wellington City and other areas. And all of these cities are unified into a single ontology, pushed through the semantic gateways to have a unified data model, and then ending up again in NGSI, on which we are then writing the dashboard application, which can utilize the data for visualizing and enabling you to monitor the cities and detect critical situations here. And last, so that's some of the visualization and some of the way how this is working. And the last point where we're extending FIWARE in the IoT chapter is to look into the edge. And basically what we can do is on the edge side, which is the lower part of this slide, we're having Docker containers where we can push dynamic code towards. We have a topology master which can monitor that edge parts and which can send functionality down there. As part of this Docker container, you can have local aggregation function, complex event processing, like Gilles is going to introduce very soon, mediation to local systems, and all of them can then locally communicate between the edge nodes and send information up into the cloud-centric or the IoT broker side here. And that system, which we're going to call FogFlow, is going to be a system in which IoT developers can specify on a very high level the topology of analytic processes they want to have. And the system is analyzing this topology and then dynamically installing that into the edge devices as well as into the cloud devices, based on profiling of the topologies and understanding how much data is sent between the different analytic components here. And basically that's ending my talk. I might take one or two questions if there's immediate one, otherwise there's a generic question and answer session later on. Not? Then.
Hello, I'm Gilles Privat from Orange, and I'm the leader of the IoT chapter. So I will be presenting something which may appear to go against the grain of mainstream platform architecture, because we implicitly assume that all platforms that we are interested in are hosted in the cloud in some way or another. And obviously this is what we have been doing in FIWARE with what we call the backend part of FIWARE, but this is also what is being done in lower level and more specialized platforms that are used as data providers for FIWARE, and these platforms also are actually hosted in the cloud. And you may end up with an architecture where actually before collecting data from sensors, you might have like 3 round trips to the cloud before the final application can get hold of the data. So what we are interested in is an architecture where it would be possible to avoid these round trips to the cloud and to operate close to the data, close to the field. And that's what we call the edge part of the FIWARE platform. And I will explain how this can work and how this answers a need for what some applications need to operate on. So this diagram shows an overall view of an instance of a FIWARE architecture that we could implement for smart city applications. And this is obviously intended to show that the edge part of the FIWARE platform is a very limited part of the overall platform. Most of the FIWARE components are still obviously hosted in the cloud, in what we call the backend part of FIWARE. And we have only this very limited and very specialized part of the platform that operates on the edge. And this is again shown on a special example intended for smart cities, but I will try to explain what is the reason and how we can actually achieve it. So the idea behind this is that we are again going against the grain of what most, especially big data applications tend to do, is they collect data and they send it to the cloud, to cloud-based repositories, whatever this data comprises, and it may comprise meaningless or noisy or totally useless data. And most applications still collect this data without filtering it in the first place. And the idea, what we try to do in this edge part of FIWARE is try to achieve some ecological data processing, filtering, cleansing data before sending it mindlessly to the cloud, as most applications again would tend to do. And this in some way or another makes up for the imbalance between the upward flow of data, which looks like a garden hose, and the downward flow of data, which looks more like a syringe, where this is the present situation for most IoT applications. So the idea, again, for what we are trying to do at the edge level is to pre-process the data and to do some kind of processing that is akin to something that has been done for quite a long time in a field of signal processing called sensor fusion. And this is more or less a very arcane domain of signal processing, because it's exclusively dedicated numeric processing that you have to implement in a specialized configuration for the type of data configuration you are interested in. But what we are trying to do is do it in a more generic way, using, as I will explain, complex event processing. Complex event processing doesn't make it possible to do the kind of sophisticated data fusion that you would like to do in, for example, robotics, or the kind of perceptual data fusion that you might be interested in some applications. But again, the trade-off is that you have something that is easy to program and easy to implement, and ideally that could be reconfigured automatically. And this is, again, the aim of what we want to achieve when we implement these applications through a platform instead of implementing them in a dedicated way. Another requirement that I want to insist on is not only the avoidance of wasteful management of data that I mentioned before, but addressing the needs of those applications that require bounded return trip times between the field devices, between the plant, what the specialist of automatic control calls the plant, the system that you actually, the physical system that you actually control, and some applications require controlling these systems with very strict latency requirements. And this is what most industrial control applications used to do with a fully dedicated implementation, and the people who implemented these kinds of systems didn't ask even the question whether there could be a problem with unbounded or non-deterministic latency, because it was implemented again in a fully vertically integrated fashion. And we still have to deal with these industrial kind of cyber-physical system applications, even though we are trying to implement them in a way that is completely different from the way they have traditionally been implemented. Again, they have been implemented as dedicated, vertically integrated applications, and we are trying to implement them through a platform like FIWARE. I won't go into the details of what we should be doing for achieving this, but we should be able to mirror the state of the physical systems that we want to control in the platform itself, to make sure that the action that we will be taking on these systems is the appropriate one, because to change the state of a physical system, you have to know the current state it is in. Because the action you will take to get to a new state depends on the current state of the system. So this is obviously something well known in automatic control. This is the very basis of the whole domain of automatic control, but people have been tending to discount this when they are using regular IoT platforms like FIWARE. So the idea behind this is that we have to implement part of the platform again in the edge domain, where this is the part that is represented here, where we can guarantee deterministic bounded return trip times between the field, between the lower part, which are the physical systems that we want to control, and the platform, which is implemented not only the representation of the entities that we control, but also the applications themselves. Because the idea in this is that the applications themselves would have to be hosted with the platform itself to ensure this deterministic latency and return trip. So I think I'm showing the same picture that Jose Manuel showed in his introduction this morning. So this is an example of a system that you might want to control in a smart city through the same kind of abstractions that we are using in FIWARE. But again, in this case, if you want to ensure that you have deterministic bounded latencies between the platform and the field devices, the actuators in this case, you would have to host it in the edge domain. And obviously, well, a lighting management application is not that latency critical, but there are other applications which are much more critical than this, and for which you definitely would need to guarantee this. So the kind of processing that we do is achieved with this enabler called the implementation of the enabler is called Cepheus. The enabler itself is called IDEC. So the name is for IoT Data Edge Consolidation. And the way it works is, as was mentioned before, there is a very lightweight broker, which is, I understand this may be partially confusing for most people, because we have now 3 brokers. We have the main Orion broker, which is a backend broker. We have the IoT broker that Erno described before. And we have this very, very lightweight broker that is meant to operate on the backend. Of course, this is the main difference with the 2 previous ones, which were meant to operate in the backend. This one, sorry, I said this one operates in the edge, not in the backend. And that's the main difference. And it's the routing. It performs some kind of routing between the data that originates from the devices. So we might also have IoT agents that would be hosted in the edge to guarantee again this kind of bounded latencies, and the processing would be performed also in the back end. So the idea behind this is that you can do all the latency critical pre-processing, the platform kind of data mediation, and the application itself on the back end. And just to finish with a more concrete view of what these kind of edge platforms could be, they span a very broad spectrum between what on the high-end side could be what we as telecom operator call next generation points of presence. These are very powerful servers that are located, as their name indicates, close to the local area networks, but they are not gateways in the traditional sense. And we could also, of course, use traditional home gateways or building gateways as hosts for these kinds of platforms. And previously in FIWARE, this, what we call now the edge domain, used to be called the gateway domain. And the reason we changed the name is precisely this, that it need not be hosted on traditional gateway in the network sense. It can be hosted in a very broad range of devices. And on the low end side of the spectrum, we could even host these kinds of platforms on Raspberry Pis or embedded servers. And we actually did test the Cepheus enabler that I described before on such low-end device. So, and of course, the idea behind this is that ultimately the whole joint backend plus edge platform should be managed transparently as what is called now a fog platform. We are not yet there, and we still have to manage the distribution between the edge and the cloud in a fixed and dedicated way, but we are moving towards the direction where this could be managed more or less transparently. So we would have a distributed platform, in a sense different from the one Erno mentioned, but distributed between backend and edge parts of the platform. So this concludes my talk.
Questions? Come on, don't be shy. There's one question over there.
So, from what we've heard, can you tell us how much is available now as opposed to what's on the roadmap for the future? In terms of the knowledge server, in terms of the centers, is all that available now for us to use, or is it coming down the track?
So the knowledge server is on the GitHub, so you can use it. Today is not my day of dealing with technology. So you probably hear me better now. The IT knowledge server is on the GitHub. You can use it. I think the scaling aspect is also on the GitHub, so the new version of the IT Broker is scaling up. And the federation aspect, to my understanding, is also on the GitHub. The edge side processing, as well as the semantic mediation and morphing mediation gateway, is part of ongoing research projects which are not yet publishing into the GitHub.
Regarding the roadmap that you mentioned, the work we've been doing so far is more to work in this cloud centralized model, right? Because this is like the very first thing you need to have. But once this is made and we see that there are enough part of the ecosystem, the FIWARE ecosystem, startups, etc., using this model, I think now is the time to go onwards. And although we've been working internally in the project for these edge distributed solutions, still we have not pushed this strongly to the community, right? But we expect the community to start to ask for these solutions where you want to deal with extended functionalities at the edge, as Erno was mentioning, and you want also decisions to be made also at the edge. So then you would like to go for a lightweight broker, etc. So the idea always in FIWARE is that you have the generic enablers, right? And you select exactly what you need. You can go from the keep it simple and stupid scenario that we presented at the beginning that should be sufficient for most of the applications today. But when you dig into IoT and you want to do something complex, then you need these edge solutions. And then we have to manage ourselves, and this will be seen in the meetings of the IoT chapter that I invite you to come in the forthcoming days here, how we will build up this roadmap. Because as this is an open community, the roadmap is under discussion, right? And everybody can express their opinion or their requirements, etc.
These were both a functional test and a stress test with a load that was, well, not with billions of sensors, but, well, with, I can't tell you the figure, but an order of magnitude of number of sensors that's realistic with regard to the applications we are targeting. Yeah, as I said, the whole thing should operate in real time, and it's meant to not add additional delays on the whole chain between the field devices and the application.
I can add to that. As I've explained to you in our fog flow area, we are using Docker container to encapsulate analytic functions. And we're also putting on the front end these analytic functions into Raspberry Pis. And running 567 Docker container Raspberry Pi, it's a matter of what is inside of the container, which is generating the load. It's not the overhead of the virtualization technique. Yes, it's adding a bit of overhead to it, but it's mainly, if you do complex event processing over a long time window, the processing overhead is much bigger, and that's determining how much the Raspberry Pi can handle.
Okay, more questions, or we can close? All right, so see you in the corridor and in the next IoT chapter sessions. So feel free to ask anything that you want to know. Goodbye, thanks.